Hello. I would like to cover a few more critical number cases. These involve, the first one would be the absolute value function. Okay. We know that the simplest form of absolute value function is this one. And this function, which is the absolute value of x. Okay. And of course, the function itself is defined everywhere, right? The domain of the function is all real numbers. But this function is not differentiable, right? So f is not differentiable as 0, right? It is not differentiable as 0. So 0 is not in the domain of the derivative. But the derivative is, exist for all the numbers other than 0. Okay, so let's draw the picture, right? This is our familiar form, f of x, absolute value of x. We're all pretty familiar with this picture, which is a V form, the V shape. Okay. This is the function. Its derivative, we also have talked about it before. The derivative is the derivative function is looking like this, right? What happened is that when we differentiate the line on the left, on the right, is equals to 1, right? Because this. Let me just give you a little more details, just in case you get lost. Okay. Wait. Piecewise function, right? And this function has just 2 rows, 2 columns. So the absolute value of x is the absolute value of a positive number is the same as the number, right? When x is greater than or equal to 0, the absolute value of x is the same as x. If x is negative, the derivative of, the absolute value of x is opposite, right? So at 0, it is not differentiable. So when we take a derivative, so basically we have 2 pieces, right? So I'm going to, these 2 pieces, okay? So this is going to be, zero, comma, 1. So that should be it. Okay, and there's another one. So I'm drawing the derivative, which is, oops, sorry. There we go. Wait, my bad. There. So the line, this line on the right, which is this one, if we take a derivative, the derivative equals to 1. When x is greater than 0. So that's a constant 1. If we take a derivative of y equals to negative x, the derivative is a negative 1, right? So let me write it down. When x is greater than 0, the derivative of f we will be taking derivative of x, which is equals to 1. If x is negative, right, less than 0, and the function, in the first case, f of x is equal to x, so the derivative equals to 1. In the second case, when x is less than 0, the f of x is negative of x. So that's why the derivative of that function when x is negative is equal to negative 1. So this is how we get these two horizontal lines on each side. But neither of them includes 0. Okay, so I'm going to draw a circle. We're going to draw a circle to indicate that. Wait, what did I do? I probably forgot to just make it red because make it red. There we go. How it doesn't show. Maybe I should two. Oh, never mind. I got it. My bad. Okay. 0, negative 1. 0, positive 1. There we go. So these are the two circles I was going to draw. Okay. At 0, the function is not differentiable. Okay. So now what's the critical numbers? Right? There's only one point that the function is defined at, but the derivative is not defined at. So the critical number in this case, the critical number, right, where the derivative does not exist, the critical number would be c equals to 0. Okay, so now let's look at this other function we have here. Okay, f is not differentiable as 0, so I'm going to put it here. Okay. So that has been proved, right? That has been proved. So this is, I just put it here, and f derivative. So this is f. All right, I'll try to make it faster, and it ended up a bit slower than I wish. Okay. So now let's look at this function. We're looking for derivative. I'm looking for derivative. Obviously, this is the same model. Same model. Okay, so the idea is pretty much the same. So if we draw this function, right? If we draw this function, there will be a turning point. There's also a turning point. That turning point is so the turning point, right? The turning point, I mean the point like 0, right? In the function, point 0, that's the turning point. To find that point is basically 3 minus 2x, equals to 0. Or you can write it in the piecewise function form. Okay, so let's write it in piecewise function form. The absolute value of 3 minus x is the same as 3 minus x if 3 minus x is greater than or equal to 0. You can see the same model. It's negative 3 minus x, 3 minus 2x, if 3 minus 2x is negative, right? It's pretty much the same model. And then we got two pieces, right? So solving this inequality, we will get x, right? So how do we solve this inequality? Do we know how to solve this inequality? Let's get a piece of scratch paper and solve it, right? So we get 3 greater than equals to 2x. So now x is less than or equal to 3/2, right? So this inequality will become x less than or equals to 3/2. If x is less than or equal to 3/2. And then of course this piece will become x is greater than 3/2, right? X greater than 3/2. So that's, if you want to confirm it, right? Just solve this inequality, right? Solve this inequality, what do we get? On scratch paper, so we got 3 less than 2x, right? Divide both sides by 2. 2 is positive, so 3/2 is less than x, right? So x is larger than 3/2. We get these two pieces of function, right? So let's look at the derivative. Okay, let's look at the derivative. And on this piece, right, you can say, oh, I want to write it differently. I want to open up the parentheses. So when I take a derivative, it's a bit easier. So distribute this negative sign inside. So we get 2x minus 3. 2x minus 3. So when we are looking for derivative, right, we need to look at all the points. The points, okay, so for x is less than 3/2, okay, without the equal, okay, we're gonna handle equal later. For x is less than 3/2, the function equals to this piece, 3 minus 2x. 3 minus 2x. And what's the derivative of it? The derivative of it would be -2, right? If x is greater than 3/2, the function would be the other piece, right? It would be 2x minus 3. So 2x minus 3. And what's the derivative? The derivative would be f of x equals to +2. Right? So when we draw, so now we have not considered 3/2. We'll check differentiability at 3/2, okay, in a moment. Okay, so let's see what's the differentiability at 3/2. We have to use the definition of derivative from left and from right? Because it's absolute value. So the derivative of function f is a differentiable at 3/2, right? So that's going to be 3/2. In this case, we have to use definition 3/2 plus h minus f of 3/2 divided by h. Taking limit. Definition. Limit as h approaching 0. Okay, what is this definition? We definitely have seen this function, this definition, haven't we? This is the definition. Okay, let's not forget about it. This is a. F of a plus h minus f of a equals to f of a plus h minus f of a, right? So it's just our a is 3/2. So we're checking differentiability, right? We're checking differentiability at this point. Now our function is this piece, right? So what is f of 3/2? Right? What is f of 3/2? Is plugging in f of 3/2. Replace x by f of 3/2. And this will give us 0. But what is f of 3/2 plus 8? F of 3/2 plus 8 is right here, right? So it's going to be 3 minus 2 times a, right? This is a plus 8. And this is f of x, right? So x will be replaced by 3/2 over 3/2 plus 8 by definition. So now let's put this above it. Okay, so that will be most natural. And what do we get here? What do we get here? What we get here is that we're going to open the parentheses, -2 times 3/2, and then -2 times 8. So we're going to minus 2h. Minus 2h. This is the multiplication. This is the multiplication. And this makes 0. This makes 0, right? So over here, we will have the absolute value of 2h. The absolute value of this negative 2h. The negative sign can be dropped. This is also essentially 2 times absolute value of h. Okay? So now let's plugging in. Let's plug in. When we plug in f of 3 over 2 plus h, we ended up with 2 times h. So 2 times absolute value of h. And this piece is what? It's 0. This is 0. Right? We have it here. We have it here. And then what do we do? And then what do we do? Right? And minus 0, we can drop it. So we ended up with something like this. How do we find limit like this? We have to look at limit from left and look at limit from right. Okay, so this limit from larger and limit from smaller, right? So let's put this piece here. Okay, so this is the larger. And that's the piece we got. Oh, sorry, we don't need that. Limit x approaching 0 from smaller than 0. So it's still the same expressions. But this way we can get rid of the absolute value sign. As h approaching 0 from larger than 0, we will get the absolute value of h is the same as h. In the other case, the absolute value of h is going to be negative of h. So this will be equals to positive 2. This will be equals to negative 2. So limit from left and limit from right are not the same, right? What can we say about this limit? So this limit does not exist. And the reason is so let's point it out to the reader, right? Limit from left. You know what I can do? I should have just done this piece. This will just be even better. Okay, So now I just want to point out that these two limits are not the same. That is to say, the limit does not exist. If it does not exist, it's not differentiable. So now let's look at the whole picture. At 3/2, not differentiable. Okay, so let's draw the conclusion. So f is not differentiable at 3/2, but it is differentiable everywhere else. It is differentiable everywhere else. Okay, and we already found the derivative. You see, we already found the derivative. So if we draw the picture, right? The first picture we can draw is about the function. And secondly, we're going to draw about the derivative, right? So this is the function. It's going to be a V shape. Is the lowest point is going to be, the lowest point is going to be, let's see. This is going to be 5. And there we go. Okay. So -2, maybe it's better. And as high as 6. If that makes sense. Okay, so this curve, and the point here is 3/2. Okay, so that's the function. That's the function. And how about its derivative, right? Derivative, for derivative, what we got here, if we organize it, right? How do we organize it? We can organize it into piecewise function. Okay, so f prime, this is 2 pieces too, right? Let's just use these 2 pieces right here, right? These are the 2 pieces, right? And how about its derivative? Its derivative is also 2 pieces, 2 pieces, okay? Taking derivative of this piece, we get -2. And this is a positive, so we took derivative. This does not include 3/2. So that's a derivative. If we are to draw the picture, okay, so that's what I'm going to do. Let's draw the picture. Oh, never mind. It should not be this one. There. This is more like it. It should be a blank. Okay. So I'm going to put it next to the function. So I'm drawing this piecewise function. Okay. Making some adjustment to the scale. And this is going to be -3, +3. And there are 2 pieces. There are 2 pieces, right? So one is 0, 2. All right. And the other there's all these circle. And there's another circle. There we go. So this demonstrates that there's a differentiability. The differentiability does not exist at 3/2. Oh, wait a second. I did it wrong. So I'm sorry. Okay, you guys, I did it wrong because it should be at 3/2. Okay, 3/2. I'm so sorry. I'm going to change it. We must change it. All right. We can change it. All right. It can be done. That's 3/2. 3/2. Okay. Wait. Okay. What do I do? Oh, wait. 3/2. My bad. 3/2 positive 2. And okay. So that circle need to be moved to 3/2. Okay. And this one will be at, I need to move that. Wait, there we go. This is 3/2, -2. There's another line. We have Here we go. Okay, this is a correct. Okay, so it's not because it's the divide is 3/2. That's the point where there's no differentiability. Okay, but you can see the similarity. It's just a shift. Okay, this picture is a shift of absolute value of x. Its derivative is also a kind of shift. Okay. So this is one of the examples I wish to cover. What is the critical number? The critical number, there are two categories. One is the derivative equals 0. Our derivative is either the derivative that exists is either -2 or +2. They will never be 0. So there's only one category for absolute value of this kind of function. That critical number is where the derivative does not exist. So C is 3/2. Okay, so that's the critical number. Let's do just I think we did this type. We did not do this type. These are some of the even number questions. So I take some and I deleted some. Let's check out Q of X. Okay. So first of all, we determine the domain of this function, which is x squared minus 9 should not be 0. Okay, that should not be 0. And as a result, x squared should not be 9. And as a result, absolute value of x cannot be 3. Cannot be 3. So in the end, x cannot be plus minus 3. All right. So that's the domain. So let's see what will be the critical number. We have to take a derivative to find critical numbers, right? So Q prime of X equals to FG, right? The denominator squared and derivative of the top is 2x multiply x squared minus 9, subtracting the derivative of x squared minus 9, that's 2x, and multiply x squared plus 9. Right, so that's a derivative by quotient rule. If we simplify it, we can factor out the 2x, right? We can factor out the 2x. So factor out the 2x, so 2x is gone. And open up the parentheses, so the minus squared minus 9, right? Minus square minus 9. So x squared and x squared is gone. Minus 9, that's minus 18. So in the end, it's a negative 36x. To find critical numbers, we're going to set Q of x equals to 0. Denominator cannot be 0. So the only chance where we get the critical number is x equals 0. 36 is not going to be, it's never going to be 0. So that's our critical number. Are there a number that's where the derivative does not exist? Well, the derivative, the domain of the derivative is the same, right? So the domain, so this is the domain, hold on. Domain of the function and domain of the derivative. Domain of the derivative is still x squared minus 9 not equal to 0. It's the same number. But there's no number that's other than there's not a number where the derivative does not exist, which are in the domain of the function. Okay. But we only just have one critical number. We just have one critical number here. Let's keep going. So you can look at the critical numbers. There are two categories. One is the derivative does not equal to 0, does not exist. The other one is a critical number. The derivative equals to 0, right? And we have the one number that derivative equals to 0 and no other numbers. Okay, no other numbers. I think we did this type in the other video. Let's look at this question, g of x to find critical number. Okay. On this question, be aware, this is a cubic root. As a cubic root, the domain for G is all real numbers. The domain is all real numbers. If it were square root, of course, it's not, right? And so we're going to take a derivative. How do we find the derivative? We're going to do chain rule, right? So we're going to rewrite this function, if you like, right? 4 minus x squared raised to the power of 1/3. Right? So when we take a derivative, we use a power rule. This power 1/3 minus 1, that's going to be negative 2/3. And then we're going to have to take a derivative of inside the parentheses, which will give us negative 2x. Near the end, when we take care of the negative exponent, so we're going to take the negative exponents, we convert it to positive exponents, which is going to be in the denominator, and the top is just a negative 2x. Negative 2x. If you like, you could put this negative 2 here, right? Negative sign here. So this will be one of the simplified form that we can see pretty clearly. And what's the domain of the derivative? The domain for derivative now, we have additional numbers that we cannot be in the domain, right? For the function, the domain is all real numbers, but for this one, the denominator cannot be 0. Cannot be 0. We haven't found the critical number yet, okay? As a result, x cannot be plus 2 or minus 2. And these two numbers is where the function is defined, but derivative does not exist, right? You can see the critical numbers. The critical numbers already include, right? The critical number already included, what are they? Plus 2, minus 2. Because those are the two numbers where the function is defined as the negative 2 and positive 2, but the derivative is not. And we have additional critical number. If we set the derivative equals to 0, we set derivative equals to 0, we get another one, right? This cannot be 0, this cannot be 0, so x has to be 0. So we have 3 critical numbers. We have 3 critical numbers. All right. All right. I think we've done something like this before, but just in case, let's do it anyway. We're gonna find critical numbers, all right? Right? So first we're gonna determine the domain. You see, this is x raised to the power negative 1/3. So it's going to be in the denominator. So the domain is that x cannot be 0. X cannot be 0. And then we're going to take the derivative, right? We're going to take a derivative. It's going to be, you can either use, quotient rule or use the product rule. And if you use product rule, okay, so let's use the product rule. You either differentiate that on this term, and then you differentiate that. And after that differentiation, actually we haven't done the differentiation, right? Power rule, right? So you're going to have a negative 1/3. Negative 1/3 minus 1. So that's going to be negative 4/3. Negative 4/3. Okay. And over here, the derivative of x minus 2 is just 1, right? And multiplied by 1, we can omit that. So how do we simplify this in order to identify the critical number? Because looking ahead, we will have to set the we're going to have to set the first order derivative equals to 0, right? We had a rule of thumb when it comes to factoring like this. Or let's use another way, use one of the ways we did before, and we just write them in the fraction form, okay, with the positive exponents, okay? So we're gonna write this as 1 over x raised to the power of positive 4/3. And this piece, we're gonna write it as 1 over x raised to the power of positive 1/3. Then it's a matter of finding common denominator. And the common denominator would be x. This piece can be written as because 4/3 equals to 1/3 plus 1. Oops. Plus 1 in the power, right? And so that can be split into x raised to the power 1 multiply x. Okay, let me write it this. Okay, 1 plus 1/3. So that's going to be x raised to the power 1 multiply x raised to the power of third, right? I'm sorry, positive third, 1/3. And what is this? If you like to write it, it's the cubic root of x. And we're going to write this as the cubic root of x. Okay, if that helps us see better. To find common denominator, we just need 3x for this piece, right? We have 3x, right? There's a -1 here. So we're going to multiply a 3x here over 3x there. So now we got a common denominator. Whichever form is make you feel more comfortable, really. Okay, I'm just going to show you one way. You figure out some other ways, and we can all be right. We can all be right. So now we have the same denominator, right? 3x. So this will make 3x because 1 times 3x. So this piece, I'm going to put it here, right? So that's the same denominator as it is here, right? There, same denominator, and remove that to 3x. So now we can add the numerator, So adding the numerator, we are getting, okay, so this part we need to be careful. This negative sign will multiply negative x minus 2. So negative x minus 2, right? We move it up there, adding 3x. So that's combined into one fraction form. And then we got minus x plus 2, right? Minus x plus 2. And combining like terms, then we get 2 plus 2x. So 2 plus 2x. And set it equal to 0, right? We're going to set, you can see in the final step, we wish to have a factored form before we can find the critical numbers. So we're going to set the first order derivative equals to 0. And to make that happen is 2 plus 2x is going to be 0. And x equals to -1. Okay. And let's look at the domain. The domain of the derivative has not changed. Okay, the domain of the derivative has not changed. We just have x times cubic root x. The domain is still x not equal to 0. So in this question, in the end, the critical number, okay, the critical number is x equals to -1. Okay. So let's work on this trig function. I'm gonna put these two beneath it. Okay, we come to it. We'll come to it. Okay, there are two more questions. So this function, the domain, obviously, all real numbers. Okay, all real numbers. There. Taking derivative, right, with respect to theta. And we get 1 plus root 2. The derivative of cosine is a negative sine theta. Okay. Set it equal to 0. Set it equal to 0. Set the derivative equal to 0. And what do we get? We get, well, if you like to write it as 1 minus root 2 sine theta, right? And so this piece is going to be 0. We're solving for theta. We're solving for theta. Okay. So as we're solving for theta, what do we get? We're going to get root 2 theta, root 2 sine theta equals to 1, right? We just move this term to the other side. And sine theta equals to 1 over root 2. 1 over root 2, which is root 2 over 2. Root 2 over 2. We know this is related to a special angle. Okay. You can, if you are familiar with those, go for it. Okay. You're gonna have lots of critical numbers. Okay. Be careful. Be careful. You're not just going to have one. We have a lot of critical numbers. So what are the angles such that sine theta equals to root 2 over 2? So those terminals would be in quadrant 1 and quadrant 2, right? So let's draw according to definition. So I'm going to do it this way because the way I covered about trigonometry, the first lesson I did not require you to know enough about special angle. So I'm going to go that route. Say if you don't know special angle, if you know special angle, you can skip this part. Okay, you can skip this part, provided you know how to find the solution. So I'm going to go by the DRA because this is the case we know D and we're looking for A. Okay, so this is going to be a case from D to A. Okay, so now by definition of trigonometry, this would be related to the definition of sine theta, right? We know all the angles are measured from that special position. So let's draw the terminal. So y equals to 0. I'm just basically getting started on a rectangular system. If you don't know the special, if you don't know this unit circle, no big deal. Wait, what am I doing here? Why is this? Never mind. Let's do it again. There we go. Okay. By the definition of red and blue. We know sine theta is related to the blue, right? Related to the blue over R. Blue over R. Okay, so obviously the blue is equals to root 2. Okay, the blue is equals to root 2. You can use the other number too, really, the same thing. Let's not doing this radical, do this, okay? Blue is 1, R is root 2. Because they're proportional, it doesn't matter, okay? R is root 2, because in the definition it says it's arbitrary point. So blue is 1, R is root 2, right? So what will be the red, right? So what will be the red? The red would be equals to the root, right? Before we do this, let me draw. The blue is 1, R is root 2. Okay, now I'm going to draw you the blue. Okay, I'm going to draw the blue. So this will be our blue. Okay, that's the blue. It doesn't look very proportional is because of the scales are different. So I'm going to make them a comparable proportion. Okay, -2, 2. This is going to be -2, +2. Okay, so this time it should be better. Let's make it a square shape. Okay. And this is the blue. I'm going to make the blue just a little bit thicker. And we know that we need to find we probably want to find the red, right? And the R. The R is root 2. R is root 2. Okay. The R is root 2. Okay. R is root 2. What's the red? The red obviously is going to be that's going to be red. There we go. Right? So this is one terminal. So this black one, this black line is a terminal for the angle theta. For such angle, for such terminal with the same blue, right? We have another one on the other side. We have another one on the other side. Okay. So we're gonna add another one. In other words, for blue equals to 1, we have 2 terminals. We have 2 terminals. Okay, so these 2 terminals are, so we have another R. We have another R. And of course, we have another red. Red. We have another red. The R is always positive. For the positive blue, we have 2 terminals corresponding to angle theta. So how many angles are there? We have 1 terminal here, another terminal there. on this terminal. Okay, so let's try to figure out what is the angle, if you will. Okay, maybe we can figure out this angle. Okay, in fact, you can see, we can find the red. Let's find the red. Okay, the red squared, right? The red squared, not red 3, sorry. The red square find plus the blue square. Blue square is 1 square, right? We already know the equals to √2 squared. √2 squared. √2 squared is 2. So red squared equals to 1. Red squared equals to 1. So red would equals to either +1 or -1. So this red is +1 and this other red is -1. So we have 2 red. So what we see here is red and blue are the same length. And so this is an equilateral triangle. And so this is, if this is, I'm sorry, this is not equilateral triangle. It's a isosceles. Isosceles. The red and blue the same length. This is a straight angle. So this is a 45 degrees, which is pi/4. Okay. So let's try. Let me mark it. So this are isosceles because this is a straight angle. So this angle is pi/4. If this angle is pi/4, measure this way, and the other angle measured terminal here, and that's going to be pi minus pi/4, right? Because this is also pi/4. Okay, so this is also pi/4. So by this time, we're ready to write down all of our critical numbers, which are the theta. Okay, so theta, we have lots of theta. Okay, we have lots of theta. Okay, one is terminating pi/4, so that's going to be pi/4 plus 2k pi. And the other one is 3 pi/4. It's pi minus pi/4 plus 2k pi. So that will cover all of these terminals and all of the angles. And of course, they are any integer. They are any integers. So those are the critical numbers. Okay, so these are the critical numbers. Those are the critical numbers. Okay. So let's keep going. You can see in the case of trigonometry situation, then we can apply our trig knowledge. We can apply trig knowledge to identify all the critical numbers, all right? All right, in this case, we have an infinite number of critical numbers. And let's do this P of T, okay? All real numbers is a domain. Okay, domain is all real numbers. From negative infinity to positive infinity. So derivative and that should give us a product rule, right? So it's the derivative t, and so e to the power derivative t is 1, right? And t, the derivative of e to the power 4t is e to the power 4t. multiply 4. Okay, so equals to, we're going to factor out e to the power 4t. And then we will have 1 plus 4t, right? When we set p prime p equals to 0, and this whole piece is going to be 0. E to the power 4t is always positive, right? E to the power 4t is always positive for any t. For any t. Therefore, this is not going to contribute anything to the product equal to 0. So when we set derivative equals 0, it's just 1 plus 4t equals 0. 1 plus 4t equals 0. And that makes t equals to negative quarter be the critical number. So that's the critical number. Critical number is t equals to negative quarter. Okay, so let's do this last one. To find critical numbers. And this is a function of u, right? This is a function of u. And domain. What is the domain? The domain of arc tangent is all real numbers, right? So the domain is all real numbers right here. From negative infinity to positive infinity. And the derivative, right? We're going to take a derivative 4 times arc10. That's going to be 4 over 1 plus u squared minus derivative u equals to 1. All right. The derivative, you can see the domain of derivative here already. And what is the domain? Same. Because 1 plus u squared, it will never be 0. Okay, so we know the domain, the derivative of domain already. So the rest is just we have to make it into a factor form. 1 is equals to 1 over u squared. So this question looks a little bit intimidating. It's not, right? It is not intimidating at all. And 4 minus 1 plus u squared. So this is going to be minus for that. Right? So that's it. Equals to, simplify, and we put it in factor form, right? 4 minus 1 is 3 minus u squared. So next, the domain is all real numbers. So we don't have this category. We only have this category. So we're going to set derivative equals to 0. Okay. Denominator will never be 0, of course. So 3 minus u squared is equals to 0. And that is and the rest is just algebra, right? So that's u squared equals to 3. Take square root, right? We get square root of u squared equals to root 3. Root 3. And the square root of u squared equals to absolute value of u. Equals to, equals to root 3. Okay, in the end, u equals to plus or minus root 3. So we have two critical numbers. Two critical numbers right here. That's all for this clip to find critical numbers of various form. And I hope this helps, even though all of these are even number of questions, you can see they're not much more difficult. Okay, thank you for watching.